All right, today we're diving into a hidden world, a world with its own secret language. We're talking about the unique signatures that every single molecule has, almost like its own personal fingerprint.
I mean, just think about that for a second. What if you could actually take a fingerprint of a molecule? And I'm not talking about the kind you leave on a doorknob. I mean, a unique, undeniable signature that tells you exactly what a substance is. It sounds like something straight out of sci-fi, but believe it or not, it's totally real.
So how do we do it? Well, the tool that makes this all possible is called infrared spectroscopy. You can just think of it as the science of chemical fingerprinting. It's this incredible way to identify compounds just by looking at their molecular signature.
So how on earth does it work? Well, the whole technique is built on a really cool idea: seeing with invisible light. Yep, we use a part of the light spectrum that our own eyes can't even perceive to uncover the secrets hidden deep inside molecules. The whole thing really boils down to 3 basic steps. First, you shine some infrared light onto your sample. Next, and this is the important part, certain chemical bonds inside the molecules soak up some of that light's energy. And finally, a detector on the other side reads the pattern of what got absorbed. That pattern is the fingerprint. But let's zoom in on step 2, because that's where the real magic happens.
This brings us to what I like to call the molecular dance. We're going to see what's actually going on at the nanoscale when those chemical bonds start reacting to the light.
Okay, the best way to wrap your head around this is with a simple analogy. Imagine that the chemical bonds holding a molecule together are like a whole set of tiny, invisible tuning forks. Each one is built to vibrate at its own very specific, natural frequency. Now, the infrared light we shine on it, that's like playing every single musical note you can possibly imagine all at once, just to see which of those little tuning forks start to ring. So here's what happens. When a bond absorbs just the right amount of energy from that light, it starts to vibrate. It begins its dance. And this isn't some random wiggle either. It's a very specific, predictable motion.
And that dance really comes in 2 main flavors. The first is called stretching. This is where the distance between 2 atoms literally gets longer and shorter, back and forth, like they're connected by a tiny spring. The other type is bending, where the angle between a group of atoms changes. You can kind of picture it like molecular scissors opening and closing.
But, and this is a big but, for any of this to happen, the conditions have to be absolutely perfect. This brings us to the real secret sauce behind absorption: matching the frequency. And here is the key to the whole thing. Absorption only happens when the frequency of the infrared light we're using exactly matches the natural frequency of the bond itself. It's just like our tuning forks, right? You have to play the exact right note to get one of them to vibrate. It's the same idea. It's a principle called resonance, just happening on a molecular scale. Now, before we get to the final piece of the puzzle, there's one more concept we need to touch on: the dipole moment. Don't let the fancy term throw you off. It's just a way of describing a little electrical imbalance in a chemical bond. Just think of it like a tiny magnet, where one end of the bond is a little bit positive and the other end is a little bit negative. And that little magnet brings us to the golden rule of infrared spectroscopy. A vibration will only show up on our detector. It will only be seen if it causes a change in that dipole moment. Think about it. If our tiny magnet is vibrating, but it isn't wobbling its magnetic field, the machine has nothing to pick up on. That change is absolutely everything, because it's what determines what we can and can't measure. Okay, so we've seen how molecules absorb light and start to dance. Now for the payoff. Let's see how this all comes together so we can actually read the fingerprint and identify the compound. This is where it all clicks. Every different type of bond, or what chemists call a functional group, soaks up infrared light at its own characteristic frequency. So for example, the OH bond you'd find in an alcohol will always absorb light at a completely different frequency than, say, a C=O double bond. They each respond to their own unique musical note. Just take a look at this. An OH group from an alcohol always absorbs way up at a specific high frequency. Meanwhile, a C=O group, which is called a carbonyl, absorbs at a different medium frequency. So by looking at our detector and seeing which frequencies are missing from the light that passed through, we can piece together exactly which functional groups are in our sample. We can, literally, read the fingerprint.
And at the end of the day, this entire process is all about helping in compound identification. It's an incredibly powerful way for scientists to peer inside a sample and figure out exactly what it's made of without destroying it. And that's a game changer for everything from forensics, identifying a tiny fiber at a crime scene, to quality control, making sure the medicine you take is actually pure.
So this amazing technique gives us a unique molecular fingerprint, a way to read a language we can't see. And that kind of leaves you with a final thought, doesn't it? If this is a molecule's language, what other invisible languages are all around us right now, just waiting for us to find the right tool to listen in?